Okay, so this is topic 7.3. It is an introduction to particle physics. So this is about answering this question, this big question. What is the matter? What is matter made up of? This is a question that has puzzled scientists for many, many years. We know the atoms, we've learned the atomic model, but the question is, how did these atoms pop out into existence? Are these real fundamental particles? So it's going to explore the fundamental particles that we have discovered, measured in nature, right? Fundamental means particles that cannot be divided into subparticles. So in the slides that I share with you, there's an introduction to this attempt to understand a theory that explains everything. That's the theory of everything. There are 3 short videos. One video talks about Paul Dirac and his famous equation. You know, this equation explains almost everything in nature, except for gravity, which is still something that needs to be completed in the standard model. And this equation, single equation, came to Paul Dirac's mind out of, he says he was contemplating fire in Cambridge. He was contemplating his chimney fire, and this equation came to his head. And apparently this equation knew more than himself, because it predicted, second video, the existence of particles of antimatter that pop out from space. Like, for example, if an electron pops out from space, a positron could also pop out from space at the same time. And matter and antimatter come from space, borrow energy from space to create these particles, and then if they collide with each other, they annihilate. So the second video, very short video to explain minute physics, to explain the existence of matter and antimatter. And the last video is quite maybe confusing, but I embrace confusion in this topic, because we need to shake our way of thinking, open our minds to different models to explain nature. So how do we explain what a force is? Well, the standard model uses exchange particles called bosons. And these exchange particles, in this analogy, is compared to money, exchange rates of money, moving from country to country, making goods move from one country to the other country. It is an analogy that uses probably economy, good for economists, but I don't think it's so easy to follow. But I would encourage you, before we start, to have a look at these 3 minutes of physics, to see if you can introduce this topic in a way that at least it creates enough confusion in your heads. Another resource that I think you could value is always Chris Donner. Very slowly you can watch this video explaining the idea of elemental particles. So these are all shared with you in the slides, so I don't have to record these videos again. It's been done. We are lazy by nature. We don't do things that others have done. So Chris Donner did a great job in explaining the nature of particle physics, and mainly what comes out of a bubble chamber. You know, a bubble chamber is a sealed container with a liquid that is at low pressure. It could be liquid hydrogen or something that easily vaporizes. So every time some energy passes through, like a gamma ray, a neutrino, a muon, the traces or the collisions that these particles have will create these trajectories in the bubble chamber. This is coming from observing the interactions of particles that come probably from space, like neutrinos or muons, traveling at the speed of light, and we capture, and by looking at the way they turn in electric fields, magnetic fields, we can learn about the nature of these particles. So the cloud chamber is one of the tools that we have to detect these fundamental particles. Of course, we also have the Large Hadron Collider as a very important tool that scientists are using to measure, detect and measure fundamental particles. So I share also a video from David Butler. You must watch this video explaining how the cloud chamber works and what have we discovered. It's very good, very important to understand how we know what we know. So what do we know? So this is something that I would like you to read with me. Down at the smallest scale, space is a constant form of creation and destruction. This is called the quantum foam. So space is not at all empty, not at all static. It's a very dynamic space that is constantly creating and destructing particles and antiparticles that pop out into existence. I like this quote from Max Planck. Max Planck, inspired Albert Einstein to introduce the idea of quanta into the nature of light. Matter originates and exists only by virtue of a force. We must assume behind this force the existence of a conscious, intelligent mind. This mind is the matrix of all matter. I love this quote. It means, in other words, if you are observing a flower, what's happening? Light from the sun interacts with the flower and then goes to your eyes, right? So this is the observer, this is the object of observation, and this is the process by which we observe. Okay, apparently, at a quantum level, all this is just one. There is no separation between observer, object, and interaction. These three are interconnected. That is why quantum physics is so interesting. And then particles of matter and antimatter borrow energy from the future to pop out into existence, only to annihilate each other and restore that energy to the vacuum almost instantaneously. These are called virtual particles, bosons. And they live for a very short period of time. All the matter in the universe is what remains from the creation of annihilation of matter and antimatter. This is a very important observation, in the string theory. The question is, okay, why is this universe material? Because if we look at the universe, it looks quite material. We don't see a lot of antimatter. We see matter, we see atoms. So there must have been some asymmetry in the early stages of the universe that explain this predominance of matter over antimatter. That is at the heart of string theory. Another, to me, inspiring book to read is The Tao of Physics by Fritjof Capra. This book is the one that brought me here to teaching physics. He uses the analogy of the Naturajan, the dancing Shiva, because he was, of course, he's a biologist he's a molecular biology and particle physicist from Berkeley University. And he narrates in this book how the dance of these particles, this cosmic dance of particles, was so similar to the ancient idea from the Vedas, the Indian philosophy, ancient Indian books that explain this dynamic universe through this image, the Shiva that is dancing. This is the rhythm of creation, the fire of destruction, in a cosmic dance that is ongoing. Very interesting book to read. Of course, it goes beyond the content of the IB, so I leave it for you to read after the exam. So matter and antimatter. As a consequence of that equation, this equation that we have here, that came into Paul Dirac's head while he was contemplating fire, this equation predicted the existence of antiparticles. That means particles that collide with matter and create energy. Of course, those antiparticles or antimatter were not ever predicted before or even in the head of any scientist. So an antiparticle is a particle that has the same mass but opposite charge. For example, if this is an electron, this is a positron. An electron has a negative charge, a positron is the same particle with a positive charge. If they meet, they annihilate. And in the same way, from space, from energy, particles can pop out and antiparticles can pop out. So this is what I was saying before, all things are connected. Pick a flower on earth and you move the furthest star. This is Paul Dirac. So a lot of this unit on particle physics will drive us into mystical quotes like this, right? So matter and antimatter were predicted. Again, the interesting thing about these predictions is that they were not expected to be. They came from equations, from a model. Same thing happened with the Higgs boson, which you will see later, and with the quarks predicted by Murray Gell-Mann. I think it was in Stanford. So when we bombarded the nucleus of the atom in long accelerators to see what the structure of the proton was and what the structure of the neutron was, we discovered these particles that were predicted theoretically are called quarks. The interesting thing about quarks is they never appear alone. They are connected to another quark, at least to one more quark. In this case, each quark is connected to two more quarks. And if you want to pull them apart, it's like an elastic band, The more force you do to pull them apart, the more force they do to keep together. So they're impossible to break down into smaller particles. That's why quarks are fundamental particles, and they can be the component of hadrons. Hadrons are hard particles that we consider big, hard, like a proton that is made up of two ups and one down quark, or a neutron made up of two downs and one up quark. So this model is what we know now as a standard model of physics. Predicts the charge of each quark to be plus 2/3 for the up, the charm, and the top, and minus 2/3 for the down, the strange, and the bottom. This is the charge of the quarks. So in this case, you have plus 2/3, minus 1/3. The proton has a charge of plus 1. And here, minus 1/3, plus 2/3, charge 0. Interesting, the mass in mega electron volts over c squared is not the same for all quarks. These quarks are all quite different. And these actually, look at this quark. The top is huge compared to the up and down, right? So these masses were also measured very, very precisely. So these are the properties of these quarks. All quarks have strangeness 0 except the strange quark, which has strangeness -1. This is another quantum number. We'll see this in a while. And then the baryon number. All baryons have baryon number 1. So what is a baryon? A baryon is made of 3 quarks, like protons and neutrons, made of 3 quarks. So the baryon number is 3. All quarks have the same baryon number, 1/3. So whenever you add 3 quarks, you have baryon number 1. So hadrons have baryon number 1. Another type of fundamental particle that was detected are the mesons, measured. Mesons like, for example, pion and kaon, right? These are baryons, the mesons, are composed of a quark and an antiquark. Like up and anti-down make a pion plus. Up and anti-strange make a kaon plus, right? So mesons are fundamental particles that are made of two quarks only. And the other fundamental particles that we detected in these cloud chambers and accelerators are the leptons, of whom we are very familiar to the electron, because these are the ones that are more stable. We see them everywhere, right? Electrons have a charge of -e. This is the mass of an electron. And since they are leptons, all leptons have lepton number 1. So electrons, muons, and taus are 3 leptons, and they come with the corresponding neutrinos. Neutrinos, very small particles, practically no mass and neutral charge. But they are energetic particles that we've seen, for instance, the electron neutrino popping out in a beta plus decay, and the antineutrino popping out in the beta minus decay. So these are particles that exist for a short period of time, very unstable, but they can go through matter. To be honest, I wouldn't say they exist for a short period of time, because they're very difficult to absorb. Okay, so these are the three big particles in nature, the small particles in nature, and then the forces, the exchange forces, the bosons. So in this model, we're going to look, for example, let's look at an interaction between two electrons. So let's make a diagram. Suppose this is an electron traveling in time. The direction of time is to the right? And this is an electron traveling in time. And then another electron is going again towards that electron. So they approach each other. These are two electrons approaching each other. What's going to happen is they're going to interact and repel each other. This is what happens. Two electrons that get close to each other, they interact. In this model, we are using an exchange particle, which is a photon known by this symbol, between the electrons. So what we say is the electron is interacting, or the electrons are interacting through a photon, and that changes the direction of the electron. So this exchange particle, the photon, is responsible for the interaction. This is the idea of the boson.